Efficient data management at scale begins with the specific structures used to hold and organize information. The Java Collections framework provides the architecture to take disjointed data and force it into a highly organized grid that software can process predictably. This framework categorizes operations into two main branches: the collection interfaces for single elements and the map interfaces for key value pairs. Looking at the single element hierarchy, logic flows from the iterable interface down into collection, where it branches into three distinct contracts: list, set, and queue. The list contract maintains insertion order and permits duplicate elements. If you insert two identical values, the structure preserves both in the order they were received. The set contract enforces mathematical uniqueness. It rejects duplicate elements, ensuring that every entry within the collection is distinct. The queue contract is designed to hold elements prior to processing. It typically follows a first-in, first-out model, processing tasks in the exact sequence they arrive. Selecting the correct base interface establishes the initial architectural constraints for your data, preventing logic errors from surfacing in later stages of the pipeline. The map interface exists as an independent branch of the framework, specialized for associative lookups. Maps rely on a key value contract. Every key must be unique, though the values associated with those keys can be duplicated across the structure. In practice, an application event log requires a list, as it must preserve a chronological sequence where duplicate event types are common. Maintaining active user sessions requires a set to guarantee that each unique user ID is only tracked once. To retrieve user profile objects instantly via unique UUID, a map provides the necessary key-to-object association. Big O time complexity provides the mathematical framework for predicting how these structures will perform as the volume of data increases. While the interfaces define the requirements for storage, the underlying implementations determine the actual speed of data access. Linear data structures require a choice between two specific memory layouts: contiguous blocks or node-based pointers. The ArrayList uses a contiguous array. This unbroken layout calculates an element's exact address, enabling O of 1 random access for reads. But inserting an element into the middle requires the system to physically shift subsequent elements in memory, an O of n operation. The LinkedList utilizes independent nodes scattered across memory, connected by forward and backward pointers. Because these nodes are independent, insertions are O of 1 pointer reroutes. However, reading a specific index requires traversing the nodes sequentially, resulting in O of n read times. This makes ArrayList a standard choice for read-heavy operations, while LinkedList is more appropriate for queue-based tasks involving frequent insertions. The internal memory layout dictates where performance bottlenecks occur, allowing developers to tune the data layer based on the application's specific access patterns. HashMap is designed for O of 1 key lookups, but efficiency depends on its ability to manage hash collisions when multiple keys map to the same location. The HashMap utilizes an array of buckets. Java calculates a bitwise index from the key's hash to determine which bucket will store the entry. Keys mapping to the same bucket form a linear linked list, making searches slow. In Java 8, when a bucket reaches 8 collisions, this list reorganizes into a balanced red-black tree. This improves worst-case lookup performance to O of log n time. Understanding these low-level mechanics prevents performance degradation in large-scale enterprise caches, where collisions are more frequent. Certain use cases require more than static storage. They require dynamic ordering and priority-based access. The priority queue is backed by a min-heap structure. When an element is added, it moves through the tree in O of log n time to ensure the highest priority element is always at the root for immediate retrieval. For sorting custom objects, developers must choose between a default internal ordering and external sorting rules. The comparable interface allows you to define a single natural ordering within the class itself by implementing the compare_to method. The Comparator interface provides an external mechanism to define multiple, swappable sorting strategies, allowing the same object to be ordered differently in different contexts. This allows you to use a priority queue for task scheduling, while applying a comparator to sort data transfer objects dynamically based on changing user requirements. Decoupling data storage from the logic used to sort it is a key principle of scalable object-oriented design. In massive multi-threaded production environments, concurrency introduces a whole new set of complexities that simple single-threaded tests will never encounter. Legacy thread-safe structures like Hashtable utilize global locking to prevent data corruption. Global locking forces every thread to wait in a single file line for any operation, as only one thread can hold the lock for the entire map at a time. ConcurrentHashMap provides a modern alternative for high-throughput environments. ConcurrentHashMap utilizes segmented, or node-level, locking. This allows multiple threads to access different segments of the map simultaneously, significantly reducing contention. Granular locking prevents the data layer from becoming a bottleneck as concurrent user numbers grow. Concurrent modification creates risks during iteration, such as when one thread attempts to read a collection while another thread is modifying its structure. Java's standard fail-fast iterators detect these structural changes and immediately throw a concurrent modification exception. Implementations like ArrayList and HashMap use this behavior to protect the read operation, stopping execution as soon as a conflict is detected. In contrast, fail-safe iteration allows a thread to complete its loop without crashing by operating on a clone of the data or providing a weakly consistent view. A more defensive approach involves enforcing absolute immutability to protect the internal state of an application from external modification. Collections.synchronizedMap creates a read-only wrapper around an existing structure, throwing an unsupported operation exception if a write is attempted. Java 9+ factory methods, such as list.of and map.of, provide a direct way to instantiate collections that are immutable by design. Mastering these fail states and locking mechanisms ensures that data structures remain stable and predictable, even under the high concurrency demands of a production environment.